Hi, this is Dr. Bricker here with some hints for homework number 2. So the first problem we have is components of vectors, and in this figure, we have several vectors A, B, C, and D, and they're all distributed here on the grid. And it's a 10 by 10 grid, which runs from -5 to +5 on both axes. First question: what is the x component of A? So for A, you can come over here and from the graph read what it is. So here's A. It has part in the y direction, which is this part, and part in the x direction, which is this part. So it looks like the x part is about 2.5. The y part would be 1, 2, about 3. So those you can just sort of read from the graph. For A, the x part is positive, the y part is positive. Now, for example, for B, the x part would still be positive, but the y part would be negative. So several questions deal with that, part A, B, C, etc. So take a look at that. The next one we have is 3.6. The velocity vector 60 degrees above the positive x-axis has a y component of 6 meters per second. Let's take a look at this. Okay, so I've redrawn it like this. Here's the overall velocity. Here's theta, which they tell you is 60 degrees. Here's the x component. Here's the y component. And the y component's actually given. So we know an angle and we know a side. We can get all the other sides, all the other angles. Of course, this is 90 degrees. So it looks like if we just go with the tangent of theta, we should be able to recover the x part. So for example, the tangent of theta is the opposite side, Vy divided by Vx, and then we can solve for Vx. So this would be Vy divided by the tangent of 60 degrees in this case. And then you can get the x part. Then you can also get the overall velocity if you wanted to. The angle, the sides. You could say the overall velocity. They don't ask for it, but I'm just giving you more information. The overall velocity squared, that would be this part here, would be the x part squared plus the y part squared. Okay, so this chapter 3 is all about vectors, two-dimensional motion. So make sure that you can handle the trig part. Okay, let's look at the next one. So the next one I wanted to talk about is 3.12, and again, you can refer to these pages here in the text. If you just click on that link, it'll pop up for you. So we need to, in part A, find the x and y components of some vector D, which is 6 kilometers, 27 degrees left of the y-axis. Express your answer in 2 significant figures. So as you go through mastering physics, try to do 2 significant figures. If you give more than 2 significant figures, it will not count it wrong. It'll just tell you, hey, you've given me more than 2 significant figures. All right, let's sketch this. Okay, so here's the 27 degrees, and this is to the left of the positive y-axis. Here's the overall vector, 6 kilometers. So here's the angle. Here's D. We want to figure out dy and dx. And again, we know an angle. We know one of the sides. We can get the other side. So let me maybe focus on getting the x part. And it's sort of a trial and error until you get good at it. Sine of theta, I'm calling this theta here, is the opposite side over the hypotenuse, over d. So then d sine of theta will give me dx. This is just going to give me the magnitude of this component. It's not going to give me the sine. So when I do this will come out to be some number less than 6 kilometers. But for me, I know it's going to have to be negative. So I'm going to insert the negative sign. There's a way of choosing the angle so that the sign will automatically come out. This would actually be 90 plus 27. But I like to work with small triangles like this and keep the picture in mind. So I'll just figure out the magnitude of dx here, just the way I've done it. And then I know from the picture that dx has to be negative. You could do the similar thing then to get dy. So the cosine of theta is the adjacent side over the hypotenuse. And then you can solve for dy. And dy from the picture is going to be positive. Okay, let's look at the next one. Okay, 3.16. You begin sliding down a 15-degree ski slope. Ignoring friction and air resistance, How fast will you be moving after 10 seconds? All right, let's sketch this one out. Okay, so here's my picture. 15 degrees. I just represented the skier as just a box. So gravity points straight down. That's G. Part of gravity is down the incline. This is the component that's down the incline. I'm calling it G in the X direction. And then this is the part that's perpendicular to the incline, and I'm calling that one G sub Y. And I'm looking at this motion like this. This is the X direction. This is the Y direction. So all of gravity isn't pulling this down, just a component of gravity. And you can imagine if when theta gets bigger and bigger and bigger, steeper and steeper and steeper, the component of gravity that's down the incline gets larger and larger. Okay, so if this is theta, this angle here is 90 degrees. This one here is 90 minus theta. And then if this whole thing is 90, that's back to being theta. So you don't have to figure this out each time. If this is theta, this is theta. So definitely on the exams, you get to make your own formula sheet. I would have a picture like this already drawn, so you don't have to go through this every time. From a little bit of trig, this part then would be G sine theta, and this part is G cosine theta. So it's G sine theta that's pulling us down the incline. Okay, well, let's take a look at this in a little bit more detail. Now that you know G sub x, that's the acceleration that's down the incline. So we can go back to any kinematics equation that we had previously. It's just that this is what we can use for the acceleration that's down the incline. Okay, so we're assuming we're starting from rest. So the initial speed is 0. So after 10 seconds, how fast are we going? What's the final speed? Good, so as I said, we could use any kinematics equation, the one that pops into my head, and we'll see if this one will work. Final velocity is initial velocity plus a times t. The initial velocity is 0. The acceleration here is g sine theta. Good, so acceleration would be g sine theta. We know the time. You can get the final speed that way. Excellent. Okay, 318 is next, and it's really similar to 316. The only thing I'll say is be careful. We're given, assume the track begins with a 55-foot long section. You just have to change that into to meters to put it into SI units. But it's the same idea. You can figure out the acceleration and then use kinematics to figure out whatever they're asking here. Actually, first of all, they ask for the acceleration. So that's similar to what we did before. And then it becomes a kinematics equation to figure out these other quantities. So knowing the acceleration, go back to your kinematics equations to get the speed here. We don't know the time in this problem, but you know the distance. So you should be able to do that with kinematics. Okay, the next one. For each of the motions described below, determine the algebraic sign, positive, negative, or 0, of the x component and the y component of the velocity of the object at the time specified. And then let's see, for all the motions, the positive x-axis points to the right, positive y-axis points up. Okay, so typical setup here. Alex, a mountaineer, must leap across a wide crevasse. And this is the first picture, figure 1. The other side of the crevasse is below the point which he leaps. Alex leaps horizontally and successfully makes the jump. Good. So we want to determine the algebraic sign of Alex's x and y velocity at the instant he leaps. Keep in mind here it says Alex leaps horizontally. So if he's leaping horizontally, he's running this way, leaps horizontally, the x velocity is definitely going to be positive. But if you leap horizontally, that means there is no y velocity. So the y velocity initially is 0. There is no y velocity. Okay, so keep that in mind for other problems. Horizontally means you do have an x velocity, but there is no y velocity. Now as he continues on his path, definitely going to pick up a y velocity, but initially there is no y velocity. Okay, let's see. Part B, determine the algebraic sign of the x velocity, y velocity, the instant before he lands. Okay, x velocity is still positive, but now he's picked up a y velocity, so that's negative. And then I'll leave part C and part D to you. Same idea, just think of the overall velocity. so we went figure 2. Determine the algebraic sign of the ball's x and y velocity the instant after it leaves the player's hand. So it's heading this way. So take a look at the sign of the x velocity and the y velocity. And same thing for part D. At the maximum height. Good, so at the maximum height, maybe it's here, we don't know exactly where it's at. At the maximum height, it doesn't stop at the maximum height. It's still going to have an x velocity. The whole trip it's going to have an x velocity. Let's sketch this part out actually, part D. Okay, so at the maximum height, it's follow this path, for example. Here's the maximum height, and then it heads back down. The entire path, it's going to have an x velocity. That's not going to change the whole time. X velocity, x velocity. I just call it x velocity. I never call it initial velocity in the x because the x doesn't change. Even at the highest point, it has the same x velocity. But at the highest point, the y velocity is actually equal to 0. So on the way up, here's the x part. It has a y part. X part's the same. Y part's getting smaller. Same x part. Y part's getting smaller. At the highest point, the y velocity is 0. So many problems when they talk about the maximum height, that sort of thing, that's the point where the y velocity is 0. So if you know that, you can solve for many different quantities. And then on the way back down, same thing, x velocity is the same, and now the y velocity keeps getting bigger and bigger and bigger. The author does a nice job of portraying this in the chapter. So again, at the highest point, x velocity is the same, positive. Highest point, the y velocity would be 0. All right, let's move on to the next one. Okay, 3.27. A ball is thrown horizontally. Okay, we're back to the idea of horizontally. That just means it has an x velocity to begin with. From a 14-meter high building, okay, with a speed of 9 meters per second. How far from the base of the building does the ball hit the ground? All right, let's draw this out. Okay, so 14 meters high. Thrown horizontally, it only has an x velocity. The x velocity will stay the same the whole time. So we want to know this distance. Now, so this is projectile motion. We've got x motion going on at the same time we have y motion going on. So here's what we know about this. From the x direction, we can't really get too much. X velocity, x distance divided by time. That's all we have. The acceleration in the x direction is 0. Scoot that up a little. Now in the y velocity, we have all of the kinematics equations. There's the first one. I just wrote it in terms of y. Velocity final squared is equal to velocity initial squared plus 2 acceleration in the y times delta y. And finally, delta y, initial velocity times time plus 1/2 acceleration in the y, t squared. Okay. So I'm trying to figure out this distance here. I called it x. You can call it delta x, whatever you want to call it. This is what we're trying to find. So from the x information, I can find that the x velocity times the time, that will give me the displacement in the x direction. So if I knew the time, I could figure out how far over I've gone this way. We're not given the time in the problem. We are given the initial velocity in the x direction, though. So hopefully from the y information, we can figure out the time, and then use that time over here. One other thing from the y direction, I know the acceleration. Okay, so we can look through here. Here's my picture. The initial velocity in the y direction is equal to 0. I don't know what the y velocity is right before it hits the ground. I do know the displacement in the y direction. If I started here and I ended up here, I'm on the ground here, and I started at a height of 14 meters. In the y direction, the displacement is actually negative 14 meters, right? Because in the y direction, I'm moving this way, which is the negative direction. Okay, so it doesn't seem like we knew a lot, but we actually do when we bring in this fact and also this fact, that the acceleration is negative 9.8. Okay, so from this information, hopefully we can figure out the time. Here's our 3 kinematics equations. This one we can't get the time from because we don't know the velocity right before it hits the ground. But it looks like this one we can actually find the time, the third one. We write it up here so you can see what I'm talking about. Initial velocity in the y times time, forgot the little y there, plus 1/2 acceleration in the y, t squared. And we're trying to figure out t. The initial velocity in the y is 0, so this whole term is 0. And then I know everything else. I know delta y. I know the acceleration in the y. I can get t. So get t from this equation, come back over here to get how far over we move. The one thing that ties together x motion and y motion is the time. Whatever happens in the x direction, it's the same time in the y direction. That's typically how these projectile motion problems go. Okay, excellent. Okay, here's another projectile motion problem. All the equations that I had listed in the previous problem work here as well. A rifle is aimed horizontally, okay, that word horizontally again, at a target 56 meters away. The bullet hits the target 2 centimeters below the point that was aimed at. Okay, good, because the bullet leaves the rifle, it's immediately under the influence of gravity, it's pulled down in the y direction. And we want to know what was the bullet's flight time, so the time, and then what was the speed that it left the barrel at. Okay, let's draw this out. Okay, so here's what I have. We've got some x velocity because it's fired horizontally. We don't know what that is, but we do know it moves 56 meters this way in the x direction, so that's what delta x actually is, 56 meters. And no matter how fast you fire this thing, it's never going to go right across here. Because it's under the influence of gravity, it's going to follow this path. And I did not draw these to scale. So the displacement in the y direction, that's the 2 centimeters. So minus 2, because in the y direction it's going this way. To put it into SI units, I'm going to have to divide by 100. So minus 0.02 meters. Another thing that I want to know a few other things. Acceleration in the y, just like the previous problem, negative 9.8. Initial velocity in the y direction, 0. Good, so this one kind of leads us through, once we get the time it takes to get here, a way of thinking about it, how long does it take to drop 2 centimeters in the y direction? That's the first part, get the time, just like we did in the previous problem. And then once we know the time, then you can get the x velocity. So all the equations that I had on the last problem, what I'm talking about, this whole section here, this is a great little section. All of these still work. So as far as the time goes, I can get the time just like I did in the previous problem. I know the displacement in the y direction, initial velocity in y times time. Luckily, same thing with this one, that term's equal to 0, plus 1/2 acceleration in the y times t squared. So the only thing that I don't know here is time. So you can get the time here, that's part A, and then we can get the x velocity. The x velocity is the displacement in the x direction divided by that time. Yeah, so if you're playing darts or anything like that, if you aim directly at the bullseye, you're never going to hit it. It's always going to fall because of gravity. What you have to do is aim above the spot and have it come back down. You don't really think about that when you're playing darts. Maybe you do a little bit, and then eventually your muscle memory takes over and you're actually throwing the dart up and having it come back down. Okay, great. Okay, so here's a Apollo 14 mission to the moon problem. Alan Shepard hit a golf ball with a golf club improvised from a tool. The free fall acceleration of the moon is 1/6 the value of the Earth. Suppose he hit the ball with a speed of 29 meters per second at an angle of 28 degrees above the horizontal. How long was the ball in flight, and how far did it travel? There's a part C also. How much farther would it travel on the moon compared to the Earth? All right, let's sketch this. Okay, so they're telling us the acceleration is 1/6 the value it is on the Earth. So on the Earth, it's negative 9.8. Divide it by 6. This will give you the moon acceleration. Initial speed of 29 meters per second. That's the overall speed at an angle of 28 degrees. So it looks like something like this. And then it comes back down. So the overall speed we're given is this part. And this has an x part and an initial part in the y direction. And this is theta. So the x part's not going to change the whole time. When you read through the chapter, they call this the initial velocity in the x. I just call it the x velocity because, again, it's not going to change the entire time. So the x velocity from this picture, initial velocity times the cosine of theta, and then the initial velocity in the y is the overall velocity times the sine of theta. So we can figure those out in this problem. Just let me give you a few other points here. The y velocity at the highest point is 0, and I'm going to call this the range. So I'm about to give you another equation called the range equation. Just keep in mind it's only good for this situation where you fire a projectile on one level and it goes to its highest point and comes back down to the same level. So this x distance, which I'm calling the range, turns out to be the overall velocity squared sine of 2 theta divided by 9.8 meters per second squared. This would be on the Earth. Maybe I should have just written it as acceleration in the y. For this problem, we're actually talking about the moon, so you'll have to substitute the moon's acceleration. So this is on the Earth. Again, figure out whatever the moon acceleration due to gravity is and put that in here. And this will tell you the range. Right? This is just the distance this direction. And you can see from the equation, what's the maximum range? Well, when is the sine function a maximum? And the sine function's a maximum at 90 degrees, or if theta is 45. So 2 times 45 would give you 90. So if you shoot this at 45 degrees, you'll actually get the maximum range. Your intuition probably told you that as well. So for this problem, it's actually easier to get the range first. So get the range first. And then we could use the x information to get the time. Several different ways of getting the time, but I would say that the x velocity would be the range, because that's what I'm calling delta x, divided by the time. So then the time, following from this, put the time over here, Vx over here, will give you the amount of time. So do part B first, get the range, and then here it's the x velocity. It's not the overall velocity here. This is just looking at the x direction. This is all x direction information. We need the x velocity. So if you're given the overall speed, you need to come down here to get the x velocity. Okay, great. So we had the list of formulas for projectile motion right here. I would add the range equation to this. Initial velocity squared. This is the overall velocity, sine of 2 theta divided by 9.8. Okay, and just keep in mind this is only good for the same picture that we just had. Okay, let's look at the next one. Okay, so for this one, last one, good quarterback can throw a football at 27 meters per second. If we assume that the ball is caught at the same height from which it's thrown, and we ignore air resistance, what is the maximum range in meters, which is approximately the same as the range in yards of a pass of the speed? Okay, so what is the maximum range? Well, use the range equation that we just came up with and use theta 45 degrees. That'll give you the maximum range. So this is the overall speed. Theta is 45 degrees. It's on Earth, so you can figure out the range. So it's really similar to the last problem. It's just you have to bring to the problem that 45 degrees does give you the maximum range. And same thing, how long is the ball in the air? Well, you know the x velocity, or you can find it anyway. So this is the overall velocity. Find the x velocity, you know the range, you can figure out the time. Really similar to the previous problem. All right, if you have any questions, just email me. You have my email address, and I will talk to you soon. Bye-bye.